Hello everybody, my name is Wonhyuk Choi, and today I'm going to be talking about reactive synthesis for non-experts, or program synthesis for musicians. This is joint work done by my advisor, Martina Lucido, and another student, Michelle Vasirani. So first, let's talk about what reactive synthesis is. The problem actually goes back all the way to Alonzo Church. Given a logical specification, can we generate a program that satisfies the specification? So synthesis should be able to find an implementation that satisfies the specification. A famous example of this is the AMBA HP bus controller, which is a standard protocol used in a lot of chips. And the protocol document is actually very long, but what researchers were able to do is write it in terms of formal specifications and synthesize a circuit that satisfies the specification. And this was heralded as a great success story of reactive synthesis. However, there was one problem that remained. Hardware engineers might be willing to write these sorts of specifications, but not everybody might want to, or even be able to write these specifications, even though reactive synthesis can be useful in a lot of different domains. For instance, in music is a naturally reactive domain, and somebody who's playing a piece of music might want reactive effects as they're playing. And how could they go about actually having this behavior encoded? They could actually code up the behavior, but the problem is, not everybody can code. And even programs who can code often have difficulty writing reactive systems. As the saying goes, it's easier to say what a system should do than say how it should be done. If only there was a way to transform specifications to programs. And this is exactly what we talked about in terms of reactive synthesis. If you can write a formal specification that encodes the behavior of the reactive system, then you can use reactive synthesis to synthesize program code. And note that this is not a trivial procedure. This is based on decades of research in reactive synthesis and more recently in synthesizing program code. But state-of-the-art reactive synthesis procedures can actually synthesize program code like this. But the problem is, who's going to write the formal specifications? The question or the statement is, reactive synthesis actually is difficult to use. It's difficult to write formal specifications. So, how do we make reactive synthesis more usable? Or, what's an easy way of writing specifications? Or, how do we even figure out what an easy way of writing specifications is? And we say, we need to create a tool. We need to create a tool that tests different interfaces and logics for reactive synthesis interfaces. And this tool should be easy for users to use so that we can easily run user studies, but it should also be easy for researchers to use so that they can easily prototype and test different interfaces rapidly. So we present the SynthSynthesizer, which is a music-based tool for prototyping different reactive synthesis interfaces. So in the tool, users want to create an audio synthesizer that adds music effects in a reactive manner, and they specify how this reactive system should behave through a specification interface. And this specification interface is exactly what the researcher prototypes, implements, or tries to test. And the user writes the specification through the interface, and this gets parsed into a logical formula. And through reactive synthesis, this gets synthesized into program code, which now controls the audio synthesizer, which behaves as the user had specified. To make things a little bit more concrete, I'm going to show three different interfaces that use temporal stream logic. And these three different interfaces are called TSL alpha, TSL beta, and TSL full. And these are the three different interfaces that we used and created using our tool. So the first interface that we created was called TSL alpha, and it uses dropdowns as a way of specifying different formal specifications. And it's very simple, it's very intuitive, it's almost as if they are if-then statements. And it only has access to a small grammar. And this is deliberately constrained so that the user can have an easy understanding and intuitive way to specify formal specifications. The other interface that we created was called TSL beta. This is also based on dropdowns, but now has a notion of time and state that are inherent to reactive systems. And this is more complex, this is more expressive than TSL alpha, and accordingly, it has a bigger grammar and more types of specifications that the user can specify. We also know that the interfaces need not be constrained to just dropdowns. We could, in the extreme, create an interface that's a written interface where users can directly harness and full expressivity of TSL. In this case, it's going to be more advanced, but due to the more complex nature of writing actual specifications, they're going to have access to a richer set of specifications that they can actually use. So with all of these interfaces, as we talked about earlier, what's important is that we need a tool to be easy for users to use. So in this case, we built our tool to be run on web browsers. And what this does is it allows the users to run the tool and the user studies without downloading anything. And if the researchers host a tool online, user studies can be run simply just by sharing a URL. And the tool should also be easy for researchers to use. So one part of the architecture diagram that we didn't cover is the actual synthesis procedure going from the logical formula to JavaScript code. And we didn't cover this because reactive synthesis procedures can be complicated. So what we've done in the tool is actually abstract this away in a Docker container so that researchers who do not have a deep understanding of reactive synthesis procedures still can try to research, okay, what's the best way, what's the best interface for specifying formal specifications, what's the best logic, and what's the best grammar for it, without necessarily needing to understand what the actual intricacies of reactive synthesis procedures are. And this is also easy for researchers to use because we make our interfaces very modular. Adding a new interface is as easy as just creating a new file, putting it in some directory, and configuring the tool to use it. On the right is actually the full 30 lines of code that actually control the TSL full interface that we showed earlier. And all we needed to do was put it in the directory and configure the tool to use this interface. And we ran a usability study with these 3 different interfaces that we showed: TSL Alpha, TSL Beta, and TSL Full. We ran a usability study with 27 participants recruited online. We asked them to watch the tutorial, use the tool, and answer questions such as, did they find it useful, intuitive, and expressive? In the presentation, I'm going to go over specific responses that the users had for different interfaces. For instance, let's start with TSL Alpha, which was the simple drop-down interface. So what some people had to talk about TSL Alpha was that they found it more to be simple and intuitive, and because it was not as complex as the other ones, some people found that it actually allowed them to do things that they actually intended it to do because it was not as complex. For TSL Beta, which was still the drop-down interface but with more complexity, some people thought that it actually was better than TSL Alpha because it had more flexibility, it had more expressivity. And some people thought that it was still intuitive, so maybe a nice balance between flexibility and expressivity and understandability. For the TSL full interface, which was the written interface, some people thought that it was more intimidating. A lot of people actually found it to be too complex for their needs and they couldn't understand what was going on. But at least one person thought that it was more complex, and that actually made it more interesting to explore. So from the 3 different interface responses that we got from the users, we can see that there's actually no best interface. We have conflicting opinions. But what we can actually say is that even though we don't know which interface is best from our user study, the only reason we got feedback is because we had a tool to test the different interfaces for reactive synthesis. If we didn't have a tool, we wouldn't even be able to receive the feedback we did and try to iterate and try to create a reactive synthesis interface, a synthesis for specifying formal specifications. So while in the presentation, I talk about qualitative user responses, in the paper, we also do have quantitative results that have more detailed analysis of user responses. In summary, I want to say that we presented the SynthSynthesizer, which is a tool for testing different logics and different interfaces for reactive synthesis. We ran a usability study with 27 participants on 3 different interfaces that we created using the tool and received feedback on these different interfaces. And at this point, I'd like to invite you all to try the implementation, which is hosted online at tslsynthesissynthesizer.com, or even try the tool. You can download the source code from GitHub and you can run the tool locally or even host it yourself online. So thank you. This was reactive synthesis for non-experts, or program synthesis for musicians.